Hello, differential equations kids. Hope you are enjoying this, or have enjoyed the weekend and are enjoying this week some. Thank you for your essays. I found some of them to be very interesting, all the ones I read to be very interesting. And again, the same thing will hold this week. If you want to do the activity on Canvas for your week's assignment, or if you want to do any of the math and just upload the math work that is associated with any of the videos, you can do that as well. So here is our warm-up to find a power series solution centered at 0 for this differential equation. And you can pause the video and then see if you get what I get, or you can do it along with me. Before I start, I do want to do a little foreshadowing for topics to come, that all the solutions, all the power series that we've dealt with already when we were making power series solutions and assuming that a power series solution would be good, there is a condition about the, oops, I don't know why I did that, condition about the coefficients that I haven't mentioned, and we don't need to really mention until we get past this topic, but so that's just a little foreshadowing. But I wanted to make sure that you know, when we are assuming, since they asked me for a power series solution, and I am assuming that I can write a power series in this form, that there is this underlying condition that has to do with the coefficients of the derivatives, second, first, and zero derivatives. Remember, since we're doing a power series, right, we are with a power series expansion, you know that the first coefficient is the value of the original function at the center, right, and this is my center, and that the next coefficient, you know, that I get is equal to the first derivative of y evaluated at 0, and that most of the time we are dealing with these as arbitrary constants because we aren't solving an initial value problem. But when we have an initial value problem, someone gives us those values. Okay? So let's go ahead and do our work. Now I'm going to skip a couple of steps here and just go right to right where I have taken care of my x to the n's, right, because I would have the second derivative and then I would have had to manipulate right where I would have to add 2 to all the indices of the second derivative, and then I subtracted 2 from here, minus, and then I'm going to distribute the 2x in, which means I didn't have to do any manipulation of this, because when I distributed the x in, I ended up getting an x to the n, and then I just have my y. Oops. So at this place, I just need to now manipulate my indices so that everybody is at a n equals 1. We're going to the highest one, which means I have to suck out the n equals 0 term out of this, leaving me with 2. I think you can do this already. 2 times 1 times c to the 2. This I leave alone. This one I have to suck out the 0 term as well, and I just get c sub 0 plus, now I can collapse all the summation notations together and factor out the x sub n. And then equating coefficients. To get everybody in terms of, to be able to get everybody in terms of those first two arbitrary constants.
In the back of the van is a string. Nothing you need yet.
Right, and I'm going to add the 2n c sub n and subtract the c sub n, and then I'm going to factor out the c sub n there. And this allows me to choose n to be 1. And I think that's as far as I went. And again, I'll leave this math for you to do. I don't know why that looked like a non-equal sign there. And then I'm going to write out my solution. And I'm going to group my c sub 0 terms. And I'm going to group my c sub 1 terms. So my first one is, right, c sub 0, put in here, and I get 1. Because I get an x to the 0, right? And then my next c to the 0 term is minus 1/2 for the second coefficient, so that's going to go with x squared. Whoops, I forgot to write these out down here, I'm sorry. This was 1/6 c to the 1. This was negative 1/8 c sub 0. This was 1/24 c sub 1. And this was negative 7 over 240. If you want to keep the factorial expressions right and write it that way, it's fine. You could write it as a summation. This one's not super easy to write as a summation, but it's not terrible either. Remember, the power goes with the, from Taylor series, right? Goes with the index. And then, of course, I get an x sub 1. I'm sorry, x to the first power. And then I'm going to group my c sub 1. And those all were with the odd powers, weren't they? Okay, so here is my solution with my arbitrary c sub 0 and c sub 1. Let's pretend that I had given this as an initial value problem, and I had told you that y sub 0 was equal to 0, and y prime of 0 was equal to 1. If I had given you that, remember, y of 0 is the first coefficient, and y prime of 0 is the c sub 1 coefficient. So plugging those in, I would get I would get 0 is equal to 0 times all of that, which would be 1 minus a bunch of zeros, plus c sub 0 plus 1 times which would mean that in this case my solution would just be, if I called this little part y sub 1 and this little part y sub 2, it's kind of like my actual solution y would be the same just as that second part. And as I said, this isn't too simple to do. It took me some while. Took a while, but I was able to write this after the x term as a summation. And let me go, and I was able to do it with the first one too, after these terms, but it was when I kept all my factorial work in here. I had to go back and do it, and you know, without canceling things out like I did to make these coefficients nice and easy. Let me just show you what that looks like. So graphing these, graphing the solution to the differential equation, what did the original equation look like? Well, here, what I have, in the red and the blue, notice what I have here is the odd terms, and this was the summation notation I came up with after the x term, and I just, for purposes here, I just put 10, you know, going from n1 to 10, but this was, and if you don't believe me, just plug and chug, see if this works, and gets all those other terms of the infinite power series, and of course this one isn't infinite, but notice that I have the coefficient being 1 here. Next I had the even, this is the even part of the solution with the even powers, which I was able to come up with a summation notation after the 1 minus 1/2 x squared. Again, this took me, you know, maybe some of you are a little bit more are faster at this than I am, but it certainly took me a while to come up with, these. But I mean, not forever, but it's not something that is immediately obvious. So I don't want anybody thinking like, no, I must not, you know, I can't come up with those so quickly, or I would have never. Don't worry about it. I only got it here so that you could see the result of what we've done. So notice that with our first coefficient equal to 0 and our second coefficient equal to 1, what the solution looks like. And can't you see the odd behavior of the solution? Isn't that kind of crazy? And of course here is the second solution, which is just 0 everywhere for every x. And of course now I can use a slider if I want, and I can change the initial condition, you know, change change this one as well. Whoa, hey, well, that's an even function now, isn't it? What if I turn both of those off and turn on this expression? What is this? Can you tell? That's where I've added them together, haven't I? But notice the coefficient of the even part of the solution is 1, and the same, and I just, so you could look at a combo of them, and I just arbitrarily chose 1 and 1. Right? Crazy. right? So there's a combo of the two with the initial condition, or I mean with both of those coefficients being 1, right? Again, that was just arbitrary. But here are the two separate pieces that we came up with. And the initial value that I actually gave you, that we actually solved for, was 1 and 0. And that's what the solution looks like. Kind of cool, right? All right, so we're not doing anything we still are staying with the same concept, really. And the only difference that I'm going to make in today's that has to do with number 23 on that handout is that so far we've always been centered at 0. So yep, you got it. We're going to now try to construct a power series solution about x equals 1. We've done this one before. This is, I hope I'm spelling his name right because I have to do it from memory. Aries? Was there an E in there? I don't remember. This is Aries' differential equation that has to do with optics. Not that I know what to do with optics that it has to do with, I just know that that's what it does, or that's what it is used for. So I start this mostly the same, with the same assumption, except when I assume a power series solution, my power series solution looks a little different. Right? Instead of having x to the n, it has x minus 1 to the n, which means I'm looking for a power series expansion that looks like this. And remember, our job, what we like to do, is to get all the coefficients in terms of the first two arbitrary ones. Right? So here's where I have started off my work, and again I've skipped a couple of steps and I've got to the part where you need to think about what to do here. And I kind of cheated. I kind of went in out of order of what we normally do because I normally distribute first, but I think you can tell here that I've already manipulated the second derivative by getting an x minus 1 to the n, right? So I've already manipulated that one because of course the second derivative started off as n minus 1 times n times c sub n to the x minus 1 to the n minus 2, right? So I've already dealt with that one and got it in with the index of 0 by manipulating my power part to a function, to a power of n. But now what to do with this red box? This is the distribution piece where, of course, I can distribute this right in here, which is what I've always done before, but do you see the issue? I'm going to be distributing in an x to the first. That doesn't combine here, right? So I have to be clever. Watch me be so clever. I'm going to rewrite this box, right? And I can't change the fact that it's an L. Crap, I forgot my equal 0. I can't change the fact that that's an X, but I'm going to be very clever with it. Oh snap, isn't that still X? So notice I've replaced the red box with this purple one, and this purple one I'm going to leave as 2 terms, which means I'm going to distribute one term and then another term through. So what does just that piece look like? Now I still have this negative out here, don't forget that. So I'm just going to deal with this part that was in front of y, right? So when I distribute the 1, to the summation, I get the same summation. But now I'm going to distribute in x minus 1. So what happens to that? I distribute another x minus 1 to the first in here, which means I still have an x minus 1, but to what power now? Yes, n plus 1. And then I still have and then don't forget this minus, so in truth, what do I have? Both of these summations are negative, right? So what do I have now? Now I kind of have to restart, and I have to try to get the same x sub n to be able to factor. So I keep saying, I'm sorry, not x sub, my x stuff to the power of n. Power of n, check. Power of n, check. Oops, not power of 1. So what happens there? Right? This one I have to adapt, but it's a different kind that we've done before, right? What do I have to do to this power? I have to subtract 1 from there, which means I have to subtract 1 from there, but that means what do I have to do outside? And now what did that create? All my powers are to the n, but my indices are no longer the same. But we know how to deal with that now. Right? We're just going to pull out our highest index is n equal 1. So we're going to pull out n equals 0 from here. Put 0, so I end up with 2 times 1, x to the 0, x minus 1 to the 0. And then I'm going to pull out an x to the 0, when n is equal to 0 here, which is going to leave me with c sub 0. And then all of these indices will be a 1. And this one is a 1, so I can put them all together. And factor out. Oh. Which means equating coefficients gets me to the fact that c sub 2 is equal to right? And then oops, I'm sorry. Thought I had a, this is positive, right? I shouldn't have skipped that because this is negative, right? So now solving 2c sub 2 minus c sub 0 is equal to 0 gives me positive 1/2 c sub 0. And then I'm going to get my recursive relationship. And I'm kind of used to this scenario here where I'm going to end up with n plus 2 times n plus 1 underneath. And then both of these were negative. So when I moved them to the other side, they became positive. And what did that allow me to do? That allowed me to get my other, right, when n is equal to 1, n is equal to 2, and n is equal to 3. This algebra was a little bit messier. C sub 3 ended up being, and again, I'll leave you to do this math. That wasn't so bad. But when I did this one, it got a little bit nastier, and I had to combine some I had to actually do some fraction work. This one was the worst. It looks so innocuous here after I did all the fraction work. It was a big pain. So what did that mean for my final solution? My final solution looked a little hairy, but I really was just looking for, right, my c sub 0 terms and my c sub 1 terms. So make some room here. I wish there was an easier way. Maybe there is a way and I just don't know it. So what did I end up with? I ended up with the solution that y was equal to the first coefficient times some stuff, and that c sub 1 coefficient times some stuff. And here's my 1/2 that goes with the power of x squared, right? Be careful, it's not x squared, it's Good. And then 1/6. And my first coefficient, or C sub 1, notice I don't just have even and odd powers like I did with the warm-up problem, right? Whoops, this is a 12, isn't it? Woot! And there is my solution. Now, it is, believe it or not, as hairy as that was, right? It actually isn't always, I mean, it has been for us, but sometimes it just gets way too nasty, and it is difficult to get, right? If not impossible, to get my solution only in terms of these two arbitrary constants. Well, I mean, I can use as many as I want, really. But, and then again, it's also in order to try to write those summation representations for these things becomes either way too heinous or ridiculously or just impossible. But for the ones that we're practicing, and that's what computers though are for, right? And programs are for, to get these. What we're doing are the kind that you should be able to do, even as kind of, you know, tedious maybe, I guess, as they've become. It's still not terrible to do. You still are able to do it, and we are able to get those solutions in terms of just the two arbitrary constants. And it just gets way uglier even faster when you aren't able to do that. Oh, I wanted to show you, before we end, I wanted to show you another technique that I've seen as I was reviewing some of my stuff from way back when. Yes, I do have notes from way back when I went. That another way of manipulating and dealing with this scenario is to, from the beginning, change your variable and say, oh, well, what I'm going to do is make t equal to x minus 1. Therefore, x is equal to t plus 1. And then I am just going to replace every, all of these x minus 1s with t's, right? So this would become a t here. This would become a t here. And this would become a x minus 1. So hopefully you can see that, right? And then you distribute your negative through, that you would end up doing the exact same thing, right? All right, well, I hope you found that just fascinating. And there is only one problem to practice, number 23. And number 23 does ask you to write the equation around the center of 1, and it also is a initial value problem, right? So not only do you need to deal with this, you will be able to find those. Remember, it usually is nicer. You make all of this kind of crappy math down here nicer if you use the values of, right, your initial conditions right away. Okay, once you get down here. All right. Have a great rest of the day/week. Hopefully I'll talk to some of you tomorrow at office hours. Take care.